Most people assume a ship sinks because too much water gets in. That's only half the story. And the half that actually kills people is the one almost nobody talks about. Think about what a modern cargo ship or ocean liner actually looks like on the inside. Most people picture it as this giant hollow shell, like a bathtub floating on the ocean. But that's not how it works at all. Ships are divided into watertight compartments that maintain buoyancy and stability in the event of a hull breach. The hull is cut up by a series of sealed vertical walls, called watertight bulkheads, running across the width of the ship from bow to stern. These watertight divisions are designed so that if one compartment floods due to hull damage, the water stays contained and doesn't reach the adjacent sections. So instead of the whole interior filling up at once, you're dealing with one isolated pocket of flooding while the rest of the ship keeps doing its job. That idea, compartmentalization, is the single most important concept in keeping ships alive. And once you understand how it actually works, you'll realize that the engineering goes way deeper than just slapping some walls inside a boat. There's math behind it, there's active human response built into it, and there's a twist at the end of all of it that completely reframes what sinking even means. We'll get to that, but first, let's talk about why this whole system exists, because the answer involves one of the most famous disasters in history, and the real lesson from it is not what most people think. The Titanic had watertight compartments. Steps had been taken by the ship's builders to ensure it would be the safest ship of its time, and the key to that was how the hull was subdivided. 15 transverse bulkheads, creating 16 compartments, each of which could be isolated using special doors in an emergency. On paper, it was an impressive system. The problem was the bulkheads didn't go all the way up. Most of them extended only to E-deck, not high enough to prevent the ship from foundering. So when the bow started to tip forward from the weight of flooding water in the front compartments, the water didn't stop at the walls. It poured over the tops of the bulkheads, meaning 6, then 7, then 8 compartments began to flood in sequence. It was like an ice cube tray overflowing, each section spilling into the next. And the whole point of having divisions in the first place was completely defeated. The Titanic sinking in 1912 exposed those vulnerabilities in compartmentation and directly led to the establishment of the International Convention for the Safety of Life at Sea, known as SOLAS, in 1914. Modifications were made to other ships after the disaster, and the height of the bulkheads on other vessels was extended to make the base compartments completely watertight. The lesson wasn't just build more walls, it was build walls that actually do the job all the way to the top. So that's the history. Now here's where it gets genuinely interesting, because modern ship design doesn't just rely on passive walls. There's a whole mathematical framework behind how much flooding a ship is actually allowed to survive, and engineers calculate it before the ship ever hits the water. Ships are designed around what's called a one-compartment or two-compartment standard. The idea is that naval architects calculate exactly how much flooding the vessel must be able to absorb while still staying afloat and stable. Large passenger ships and warships are held to a stricter standard than cargo vessels because the number of lives on board is higher. And the real safety margin built into all of this is something called reserve buoyancy. Every ship is built with more volume above the waterline than it strictly needs to float. That extra volume is the buffer. It's what gives the ship room to absorb a flooding in one or two compartments without losing all of its lift. Naval architects calculate exactly where that limit is, and the entire compartment layout is designed around it. The position of the bulkheads along the length of the ship is primarily decided by floodable length calculations during the assessment of damage stability. This isn't guesswork, it's precise engineering done before a single piece of steel is cut. Now, passive walls and math are only part of the picture, because when a ship actually takes damage, the crew doesn't just sit back and let the design do its thing. There's an active layer of response built into every modern vessel, and this is where things get really practical. Watertight doors are a huge part of it. On modern warships and large ships, the heavy sealable doors between compartments can be closed from a local lever right there in the passageway, or remotely from a central damage control station. That means the crew can isolate a flooded section within seconds of an alarm going off before the water has a chance to spread. And remember, the Titanic's bulkheads had doors in them too, because it simply wasn't practical to expect passengers to climb a staircase to get over a bulkhead, so doors were put into the bulkheads to allow access, immediately removing the ability to keep a flooded compartment isolated from the next. Modern ships solve that problem with doors that seal under emergency conditions rather than staying open by default. Beyond the doors, ships carry powerful bilge pumps and dewatering systems that actively fight incoming water. Rather than just containing flooding passively, these systems can remove water faster than it enters through a smaller breach, buying the crew time to reach port or make repairs. And on warships especially, there are dedicated damage control teams, people whose entire job is to patch hull breaches, shore up bulkheads under pressure, and manage flooding in real time. Simple measures can stop flooding, such as locking off the damaged area from other compartments, or blocking the damaged area by wedging material around a tear in the hull. It's a physical, hands-on fight against the ocean, and it's a trained specialty, not something that happens automatically. There's also a newer layer on top of all of this. Modern ships increasingly use flood sensors and water level alarms built directly into compartments. These alert the crew or damage control systems automatically, so the response starts the moment water enters a space, not minutes later when someone notices a problem. Digital twins, virtual replicas of a ship's hull and bulkhead network, could enable near real-time damage assessment and more precise stability management under a wide range of conditions. The ship is essentially watching itself. And then there's the double hull. The 1994 MS Estonia disaster highlighted vulnerabilities in certain ferry designs that led to rapid capsizing and resulted in stricter regulations for new builds to mitigate progressive flooding risks. Double hulls are now standard on tankers and many large vessels, an inner and outer hull separated by a void space, so a grounding or minor collision has to breach two separate layers of steel before it reaches anything critical. It became mandatory internationally after major oil spill disasters made the environmental and safety cost of single-hull designs impossible to ignore. Some modern warships take this even further with what's called a citadel design, where the most critical spaces, the command center, the propulsion systems, the power generation, are clustered together and given extra reinforced watertight protection, essentially a ship within a ship. Even if the outer sections flood completely, the core keeps functioning. The vessel stays in the fight. Okay, so we've covered the passive design, the math, the active response systems, and the modern innovations. But here's the thing I mentioned at the very start, the part that most people never realize, and the part that actually explains why ships are lost even when the design does everything right. A ship can be technically floating and still be doomed. Because the real danger from flooding is often not volume, it's balance. Ships often capsize rather than simply sinking lower in the water, and this was frequently due to off-center flooding that caused a severe list, made worse by the free surface effect of water moving around inside a compartment. When flooding happens unevenly, say water fills compartments on the port side but not the starboard side, the ship starts to lean. And if that lean gets bad enough, the vessel rolls over while it's still technically buoyant. List, or capsizing in the ultimate case, is due to unsymmetrical flooding or a combination of that and negative stability. This is why counterflooding is a real damage control technique. Counterflooding is the act of deliberately flooding compartments on a ship to balance the list. If a ship is damaged and begins to lean to one side, compartments on the other side can be intentionally flooded to correct it. So, you're trading a bit of extra weight for stability. You're making the ship heavier on purpose, to keep it level, because a level ship that's riding low is far safer than a buoyant ship that's about to roll over. All 6 British pre-dreadnoughts that were sunk by torpedo attack during World War I capsized, not because the flooding overwhelmed the hull, but because the flooding was uneven and the list became unrecoverable. The water got in and the ships tipped. That's the real threat. And it's why naval architects don't just design compartments to limit how much water gets in. Damage stability evaluates post-flooding behavior specifically to prevent capsizing or sinking. The compartment layout is designed to control where water goes and how the ship responds to it, not just to slow down how fast the interior fills up. So here's what we actually learned today. Ships survive flooding because they're divided into sealed compartments by watertight bulkheads. Not one hollow shell, but dozens of isolated sections. The Titanic proved that those bulkheads have to go all the way up, and that lesson rewrote international maritime law. Modern ships layer active systems on top of that passive design. Watertight doors that seal in seconds. Pumps that fight back against incoming water. Dedicated crews trained to patch and shore up damage in real time. Double hulls that force water to breach two barriers instead of one. And the engineers behind all of it aren't just calculating how much water the ship can hold. They're calculating how the ship moves with that water inside it. Because staying level matters just as much as staying afloat. The thing that actually sinks ships isn't always the size of the hole. It's whether the crew can keep the vessel balanced while the water comes in. That's the hidden design, and now you know it. If you want to see how a completely different kind of vessel solves a completely different survival problem, the video on how submarines manage their systems is right there, and it has a similar twist ending that I think you'll appreciate. Drop a comment below telling me which part of this surprised you most: the Titanic's actual design flaw, the counter-flooding technique, or something else. And if you're not subscribed yet, now's a good time. This channel goes deep on exactly this kind of engineering that most people never think about until they really need to.